Hi, my name is dr.ahmath. In this video lecture, we are going to discuss about the vectors and the angles between the vectors. We'll derive the formula which will allow us to find the angles between the two vectors, and also we're going to discuss how to find or how to define the perpendicular or so-called orthogonal vectors, and also how to identify the parallel vectors when we're talking about the position vectors. So first of all, so let's say we are given two vectors. So let's say U and V. Well, if they start from the same point, then we are interested to find the angle between them. Okay, so then the angle between them can be found using the following formula. For example, the cosine of the theta is going to be equal to U transpose the V divided to the norm of the U, norm of the V. So let's do first of all an example how we can find the angle between the two vectors before we proceed to derive this formula. So in this example, let's say we're given two vectors. U was the components 1 and 2, and V was the components minus 2 and 1. So I'm interested to find the angle between them. So in order to do this, I will calculate all of the ingredients of this formula. So basically, I need to multiply the U transpose to the V, which is going to be a 1 and 2 times T is a minus 2 and 1. Then we need to calculate U norm, so which is going to be square root of U transpose to the U, right? So we just discussed previously that the norm of the vector in a square is this vector is multiplied to itself as an inner multiplication. And the V norm is going to be equal to the V transpose to the V from the square root. So let us multiply them. So there's going to be square root of 1, 2 times to the 1, 2, which is going to be a 1 times 1 plus 2 times 2, which is going to be square root of 5. So we are going to get the same result or a similar result when we multiply the V to the V. So T1 times to the minus 2 and 1, it's going to be minus 2 minus 2 plus 1 and 1, it's going to be a square root of 5 again. So if you multiply these two vectors, U to the V, it's going to be 1 times to the minus 2, which is minus 2, plus 2 to the 1, which is going to be plus 2, and this is equal to the 0. So now if I put everything down to the formula, so the cosine of the theta, the angle between of them, is going to be equal to the U transpose to the V divided to the norm of the U, norm of the V. Well, so if we've just found that the U transpose to the V, it's going to be equal to the 0 divided to the square root of 5, square root of 5, which is going to be equal to the 0. Well, the angle between these two vectors, or the cosine of the angle between these two vectors, is equal to the 0. So that is why the theta is equal to the pi over 2, since cosine of pi over 2 is equal to the 0. So let me draw these two vectors in order to try to understand whether this formula is true or not. So I've got a rectangular coordinate system again. So if you remember, the U was the vector was the coordinates 1 and 2. So I need to find the point 1. We need to draw the point 2, and this vector here is going to be this vector. So this is U was the coordinates 1 and 2. So at the same time, we've got a vector with the components minus 2 and 1. So it's going to be minus 2 in this direction and 1. So this red vector is going to be V with the components minus 2 and 1. And the angle between them is actually 90 degrees, where the cosine of the angle between of them is equal to the 0. Well, this formula is extremely important for us, which allows us to find the angles between the two vectors, and also which allows us to define the perpendicular or orthogonal vectors using a scalar multiplication or the inner multiplication. You can see here that, hey, if the two vectors are orthogonal, then their multiplication U transpose to the V is equal to the 0, because it makes the cosine of the angle between of them to be equal to the 0. So this is like important consequence. So now let's go back to our formula. So what I would like to do is I would like to go a little bit more deeper, more theoretical, and try to prove this formula. So in order to do this, we need two things. We need to know how to subtract the t vectors geometrically, and also we need to know so-called cosines theorem. So let's write down the theorem, and we're going to prove this theorem. So we're given t vectors u and v. So in general, this formula works in any dimensions. So, but let's do this for the 2D or for 3D. So 2D, let's say, then the cosine of the angle between the two vectors is going to be u transpose v divided to the norm of the u and norm of the v. So we are going to prove this theorem. So let's say we are given two vectors. So this is going to be u, and let's say this is the v. So if you remember, if we put two vectors starting from the same point, and if we connect their ending points, what kind of vector we get is u minus v, for example. Okay, so if this is u minus v, then the direction is going to be like this, because so the direction of the subtraction is always coming from the negative vector to the positive. So in this case, v is negative, so that's why it goes to the u, right? So from negative to the positive. Okay, so and also we are given this angle, cosine or theta. So I would like to connect all of these terms here. So first of all, okay. So first of all, let me try to find the norm of the u minus v in the square. So the norm of the u minus v in the square. So if you remember, last time we discussed this as well, like in the previous videos, we discussed this as well, like the norm of a vector in the square is the vector is multiplied to itself, okay? So I just would like to find the norm of the u minus v in the square. So if I would like to find a norm of any vector in the square, I just need to multiply this vector, because this is a vector, right, to itself. So I'm going to multiply u minus v transpose to the u minus v. So I'm just going to open up all the brackets. It's going to be u transpose minus v transpose times u minus v. So I'm going to multiply every term of the first bracket to every term from the second bracket. It's going to be u transpose to the u minus u transpose to the v minus v transpose to the u plus v transpose to the v. At the same time, we know that the u transpose to the u, it's a norm of the u in the square, right? So minus 2 u transpose to the v, because the inner product doesn't matter. So if you change the order, then it is going to be the same result, plus the norm of the v in the square. Okay, so you see, so here I don't have anything like a cosine. So well, here in the formula, I have a cosine. So we need to figure out how to connect the cosine of the angle and this vector u minus v. So in order to do this, we're going to use so-called cosine theorem. So if you remember, the cosine theorem tells you is about the triangle. So let's say we've got the lengths of the three sides, R, A, B, C. They are the lengths, and this is gamma. So the cosine theorem tells you that, hey, cosine of gamma is equal, it basically tells you that the c in the square is equal to the a in the square plus b in the square minus 2ab times cosine of the gamma, right? So where a, b, and c are the lengths of those sides of the triangles. So now, so we've got the similar triangle here, right? So let me just try to copy this out. So we've got a similar triangle here. Okay, so I'm going to use the same theorem in order to for this triangle. Well, I can't just use the u. I can just like write down u minus v in the square, right? Because this is not a scalar. So here, C is a scalar, just a number, while U minus V is the vector. So we can't really square a vector, we can square its norm, right? So the length of the vector, which is opposite to this angle theta, is equal to the length of the U in the square plus the length of the V in the square, right? Minus 2, the length of the U, the length of the V, and the cosine of the theta. So these two formulas are the same, right? So we use the cosine theorem here for the vectors. So now what I would like to do is, so we've just derived here this formula, which was like a just expansion of the U minus V norm in the square, right? And at the same time, I've got the same equation. So I've got another equation for the same term. Okay, so I would like to equalize them. So this is equal to this from one side, and this is equal to this from another side. So they should be equal, right? So they are the same. So I'm going to equalize them. So let's make it smaller. So it's going to be the norm of the U in the square minus 2 U transposes a V plus the norm of the V in the square should be equal to the norm of the U in the square plus the norm of the V in the square minus 2 U norm, V norm, and the cosine of the angle between them. Okay, so they are equal because they are both equal to the norm of the U minus V. So U minus V's norm in the square. So here I'm going to cancel out some of the terms. So this is going to be canceled with this one. This is canceled with this one. And even minus 2 is going to be canceled with the minus 2. And what is left is U transposes a V is equal to the norm of the U, the norm of the V, and the cosine of the theta. So from here, we can find that the cosine of the theta is equal to the U transposes the V divided to the norm of the U, norm of the V. Okay, so this is the proof, which is like quite interesting, but at the same time like intuitive. Okay, so there are couple of consequences of this formula. But the first one is it allows us to define the perpendicular or so-called orthogonal vectors. So let's write down the definition. So it is going to work, this definition works for any dimensional vector. So we are given U and V from any dimension, n-dimensional vectors, for example. So these two vectors, they are called orthogonal if the U transposes a V is equal to the 0, okay? If the scalar multiplication is equal to the 0. And that is clear from this formula, right? So whenever they are perpendicular, then the angle is going to be equal to the pi over 2, and the cosine of the pi over 2 is equal to the 0. So this term should be equal to the 0, and this is equal to the 0 when the U transposes a V is equal to the 0. So let's do a small example in a 3D, for example. So let's say I've got a 3-dimensional coordinate system. Right, so let's say this is going to be, anyway. So this is X, Y, and Z, okay? And I've got two vectors. For example, this vector is going to have the coordinates, let's say it's going to be U was the coordinates 2, 0, 0, okay? Because it's along the x-axis. And let's assume that, for example, this vector, V, is going to have the coordinates like a 0, 0, 3, for example, along the z-axis. Okay, so it's clear from the picture that they are perpendicular. Okay, so at the same time, so if you just multiply the U transpose to the V, it's going to be equal to 2, 0, 0 times to the 0, 0, 3. And their scalar multiplication is going to be 2 times 0 plus 0 times 0 plus 0 times 3, which is equal to the 0. Okay, so the two vectors are perpendicular. So in the higher dimensions, we call this the orthogonal vectors if their scalar product is equal to 0. So and it works in the inverse direction as well. So it's like if the scalar product is equal to 0, then the vectors are perpendicular. So we know how to define the perpendicular vectors. It's also important for us to define the parallel vectors. Okay, so this is the definition about the orthogonal vectors. Orthogonal vectors. And now let's discuss the parallel vectors. Okay, so previously and from the school, we defined the two lines as parallel if they never intersect, right? So with the vectors, the situation is slightly different because, so we're talking about the position vectors. So do you remember that position vectors, they all should start from the same point. So basically, if you just take these two lines and put this to the origin, right? Because we can now place the vectors, right? So let's assume that this is one vector, this is another vector. If you would just put them to the origin, then they are going to be quite similar, right? So for example, if the length is slightly different, then they're going to be like this. So now we need to figure out how to define the parallel vectors because it's obvious that the parallel vectors should lie on each other, right? So how to define this mathematically? So if you remember, we said that, hey, this is the u and this is the v. So does these two vectors are different in terms of the direction? No, so they have the same direction. So the only thing which is different for these two vectors, or which might be different for these two vectors, is the lengths. So, and how do you remember how to change the lengths of the vectors without changing its direction? So if you're just given a vector, if you just would like to make it longer twice. For example, let's say you're given a vector u with the coordinates 2 and 0. What's the length of this vector? So the length of the vector, if you remember, it's going to be 2 in a square plus 0 in a square, then you need to sum them and take the square root, which is going to be equal to the 2. So if you would like to create a vector v, which is going to be twice longer than the u, you are just going to multiply this vector to the 2. So twice multiplied to the 2 is 0. So this is going to be 4 and 0, and the vector of the v, its length is going to be equal to the 4. Okay, so these two vectors u and v are going to have the same direction. So if you would like to just change the lengths of the vectors, then you just need to multiply them to the constant. So the two parallel vectors, two parallel position vectors are going to lie on each other. So that is why, in order to get the v, you just need to multiply the u to some constant, right? For example, in this case, maybe u is slightly more longer than the u, so 1.5 times, for example. Then if it is possible to just multiply the u to some constant and obtain the v, then in this case, these two vectors are going to be parallel vectors. Okay, so this is the definition. So the parallel vectors means like there exists a constant k from the real numbers so that the k times u is equal to the v. So in this case, the two vectors are called the parallel vectors. So let's do a small example. So let's say we are given a vector u with the coordinates like 2 and 4, and we're given a v vector with the coordinates 3 and 6. Okay, so it's kind of clear that the c vectors are parallel, right? Because if you multiply the u to the 3/2, then you're going to get a v. So let's check this. So basically u is 2, 4. If you multiply this 1.5 or 3/2, it's going to be 3 times 2, 3/2 times 2, 2, and 3/2 times 4. So on the top, we are going to get simply 3. On the bottom, we're going to get the 6, which is the same as the v. And we can just draw those two vectors and try to see whether this is true, right? So a vector with the coordinates 2 and 4 is going to be like this. So 1, 2, 1, 2, 3, 4. Oh, it seems it's going to be difficult for me to draw them, to sketch them. And the vector with the coordinates 3 and 6 is going to be on the top of this, so it's going to be somewhere here. So something like this. Okay, so this is going to be v, which is simply 1.5 times longer than the u. So this is how we're going to define the parallel vectors. Well, this is it about today's lecture. We discussed about how to find the angles between the two vectors. We discuss what is the orthogonal vectors, what are the parallel vectors. So in our next lectures, we're going to discuss about the theorems, about the norm and the angles, like a couple of important theorems on calculus, which are going to help us to work with the more difficult and theoretical topics.